So let's have a little conversation about how the Paleozoic era ends, and it is spectacularly. So let's start with a conversation about the Carboniferous. The Carboniferous is what geologists in most of the world call what Americans call the Mississippian and Pennsylvanian periods. And that's because in the United States, the Mississippian and Pennsylvanian periods are significant and different. So let's start with this paleogeographic map. This should look a little bit familiar because we talked about a similar one in the Devonian. So you can see again the Acadian highlands here and your equator. And then the antler highlands here are above sea level. But you see all this transcontinental arch that we talked about in the Devonian, no longer above sea level. And instead we have a vast inland sea that is in this light green that covers the vast majority of the continent. And so in general, all across most of North America really, in the Mississippian, limestone is deposited, and it's deposited in what geologists call an epicontinental sea. So I also wanted to take this opportunity to teach you this word. So epi means on top of, continent. So when sea level is high, like it was during the Mississippian, you have parts of continental crust that are inundated with seawater. And so this is an epicontinental sea because the sea is above the continent. This epicontinental sea is part of the Kaskaskia transgression that began in the Devonian and started all of those, the deposition of all of those energy-bearing units that we discussed in our last video. So while there was an abundance of limestone deposited during the Mississippian, in the Pennsylvanian period in the United States, there were extensive deposits of coal. And the coal was deposited in what appeared to be evidence of cyclical transgressions and regressions. Again, often associated, and they're called Pennsylvanian coal cyclothems. So Pennsylvania doesn't necessarily refer to the state, although there's certainly plenty of coal in Pennsylvania, but it's this coal cyclothem that we're going to discuss on this slide. So in this diagram, what you can see is that there's a series of non-marine sediments that are deposited when sea level is low. So you get your sandstones, shales. There is some examples of limestones that are also deposited in freshwater. They're much rarer, but they occur. And then, so this is a regression. And at the top of the regressional layers is typically a layer of coal. Coal is deposited mostly in swamps. And so you have basically stuff that's on land, and then right above sediments that were deposited on land, you have predominantly marine rock that is deposited on top. So here we have limestone and shale. So we have these packages of rocks where we have non-marine rocks with a coal cap and then marine rocks. And this cycle is repeated throughout the Pennsylvanian period, and it's directly related to the growth and melting of ice sheets. So when you have growth of ice sheets, that's when you have your regression, right? Because sea level is lower as ice is stored on land or water stored on land in the form of ice. And then you have melting, and that's associated with your marine portion of the cyclothem. The thickness, which is really cool, you can correlate to the Milankovitch cycles. I'm going to show you two short videos about the Milankovitch cycles. I think the first one will do more science-y, and then the second one will just be, you just have to humor me with the second one.
This is our climate. What do I mean? Most of us have heard of the ice ages from movies.
Everybody down!
20,000 years ago, places like New York City were covered in ice. But that wasn't the only time. There were a bunch of ice ages, going back millions of years. And here's the crazy part. By looking at cores of mud from the bottom of the ocean, we can tell that these ice ages actually came and went on a schedule, like clockwork. In fact, the entire world got hotter and colder with the ice ages. So what caused these huge swings in Earth's climate? Actually, it was clockwork, corresponding to slight shifts in Earth's orbit, now called Milankovitch cycles after the Serbian scientist who started to figure this out. We know that the gravitational pull of the sun, moon, and other planets makes the Earth's axis wobble like a top on a cycle of about 20,000 years. The tilt of the Earth also shifts about every 40,000 years. And the shape of Earth's orbit around the sun goes from more circular to more like an oval on a schedule of about 100,000 years. All of these changes affect how heat from the sun warms the northern hemisphere where ice sheets can grow. So, the same types of planetary movements that create our days, weeks, and years actually seem to also create something like superseasons, our climate. But that's only part of the story. Because with the orbital cycles, when the northern hemisphere warms, the whole planet warms. And when the northern hemisphere cools, the whole planet cools. Changes in Earth's position set the tempo of the climate clock, but they don't explain why the shifts in temperature are so extreme and why they're global. Going from times when New York City could be covered in a thick layer of ice to times like today, when it hits 100 plus in summer. So what else is going on here? A major clue came when scientists extracted cores of ice from Antarctica, dating back hundreds of thousands of years. And inside of them were trapped little air bubbles of ancient atmosphere. They revealed the amounts of carbon dioxide in the atmosphere going back 800,000 years. Remarkably, the rhythm of this record matches that of the ice ages recorded in the ocean muds, almost perfectly. We know that CO2 is a greenhouse gas, a gas that traps heat on the planet. So this could explain those huge global shifts. But where did the CO2 come from? Why would gas in our atmosphere match the tilt and wobble of Earth? This is where that can of soda comes in. These are carbon dioxide bubbles, now visible because I just depressurized the can of soda. One theory is that as the ice sheets melt, they release pressure on the world's volcanoes, setting them off like a freshly opened can of soda. But that can only account a little bit for what was going on. Another theory is that the oceans act like a sea of soda. How do I get a ton of bubbles to come out? By stirring it up. The same thing happens with the world's oceans. They also contain carbon dioxide. And our planet, the blue marble, is 70% ocean. Now, even though a can of seawater doesn't have quite as much carbon dioxide as a can of soda, that's still a lot of carbon dioxide in all of the world's oceans. And when ice sheets start to grow, that changes everything. The wind patterns change, which shifts ocean currents, and that changes how the ocean mixes. Scientists believe that the biggest reason CO2 tracks the orbital cycles is because when the planet warmed just a touch, that enhanced ocean mixing. And then just like our stirred soda, the oceans lost some of their fizz to the atmosphere. And more CO2 in the atmosphere meant more heat trapped on the planet. But today there's another source of carbon dioxide. Every year, humans dump over 30 billion tons of carbon dioxide into the atmosphere. That's well over 50 times the amount that comes from volcanoes. As a result, we're warming the planet 10 times faster than anything we've ever seen before. The tight link between the orbital cycles and the atmosphere is gone. We've actually broken the climate clock.
Good job breaking the climate clock, people. All right, so this is a creative illustration of the Milankovitch cycles. So here's the Earth's wobble, its precession. And this really impacts the distance of the Earth to the sun in summertime and wintertime. Obliquity is the tilt of the sun, which controls how much how intense the angle is at the poles of solar radiation. eccentricity controls basically the distance between the Earth and the Sun as it transitions from elliptical to more circular. Beautiful. All right, good stuff. So that was the Carboniferous, again, the combined Mississippian and Pennsylvanian period. Now let's talk about the Permian. The Permian, there's all sorts of stuff going down. First of all, there's the Allegheny and orogeny, which is the last pulse of orogenic activity in North America to create the Appalachian Mountains. It results in the formation of our most recent supercontinent, Pangaea. And here is a reconstruction of Pangaea. You can see it's centered along the equator, and it occurred with the closing of what's called the Iapetus Sea. The Iapetus Sea is the proto-Atlantic Ocean, so prior to the Atlantic Ocean opening. So this is just a series of ways that this reconstruction occurred. So we can map out where desert and evaporites were found, and we know that those locations had to be about 30 degrees north or south of the equator. We can figure out where the glacial deposits are, knowing that those will be thickest at polar regions, especially since we're primarily centered along the equator. We can use fossils, right? There are organisms that we know live on land, that are some that live in water, some only live in warm temperatures, some only live close to sea level, things like that. We can use coal deposits because we know coal deposits are common in warm climates. We have all the things that Wegener talked about, right? The fit of the continents, the matching mountain ranges between North America and then up through the mountains here in the Caledonian Mountains in this region, as well as the Atlas Mountains in northwestern Africa. And another tool that geologists use is called paleomagnetic data, and that has to do with fluctuations in the Earth's magnetic field. So when lava flows, iron-rich minerals will align itself with the magnetic field, and then those are sort of frozen into place as that lava cools. So as the magnetic field fluctuates, subsequent lava flows will line up to where the new magnetic North Pole is, or the magnetic South Pole, as the case may be. So I have two little videos to show you. The first one illustrates how we can figure out changes in the magnetic field, and then the second one has to do with how we actually sample that paleomag data.
Switched. When the rocks in the oceanic crust are formed, they preserve the direction of the magnetic field at that time. If it matches the direction of today's magnetic field, it can be measured as a positive anomaly. If the direction of the magnetic field is opposite, it can be measured as a negative anomaly. However, even this revelation doesn't explain the stripes on the seabed. To form stripes of alternating positive and negative anomalies, different parts of the seabed would have had to form at different times. In fact, the whole seabed would have had to have moved over time. In the Atlantic Ocean, the magnetic stripes are symmetrical on either side of the mid-Atlantic ridge. Rocks on either side of the ridge have preserved the imprint of the current magnetic field and are geologically the youngest rocks in the Atlantic. As we look further away from the ridge, we observe the well-developed magnetic stripes. We can also see that the rocks get geologically older toward the eastern and western edges of the ocean. This model demonstrates how the seabed itself must have moved over time. The two strips of paper represent sections of oceanic crust that emerge from a mid-ocean ridge in the centre. As molten rock is erupted at the mid-ocean ridge, it cools and solidifies, preserving the orientation of the Earth's magnetic field. Then the orientation changes, the magnetic field flips, and this change is recorded in the younger rocks. As more and more rocks are added in the centre, the oceanic crust spreads further and further out. The magnetic stripes develop as the magnetic field keeps flipping back and forth. In the Atlantic Ocean, this whole process took 200 million years. It was very, very slow going. In order to produce the pattern of magnetic stripes that was discovered in the 1950s, the seafloor had to spread out. The Atlantic Ocean actually grew over 200 million years, and the continents on either side had to separate from each other. It sounds crazy, but this is the only reasonable explanation for how the magnetic stripes were formed. Actually, that sounds a lot like Wegener's idea of continental drift, except it was given a new name: plate tectonics.
Oh yeah, that's right. I'm sure you
What do you
remember.
think-
But as the continental drift hypothesis merged with the seafloor spreading hypothesis, it became the plate tectonic theory, which is awesome. So we can find rocks and find the iron-rich minerals in them. We use something called a magnetometer, and they indicate which direction that they were pointing. So we can do these paleo reconstructions to figure out where the magnetic North Pole was at certain times and where those locations were relative to the equator. Let's see. What other fun things are they going to say here? Here's just a short video showing you how loud and obnoxious it is when we take paleo mag samples, basically with sometimes a water saw, and buzz through rocks, and we can pull out these circular samples, carefully measure their orientation, and then we can record and measure, once we look at the iron-rich minerals, which direction the iron-rich minerals are pointing, knowing that they used to be pointing towards their magnetic North Pole. This is nice to do in igneous rocks, like in the seafloor, simply because they're igneous, so you can also do radioactive dating to get a really accurate age. And those flips in the magnetic field, not just drifting of the magnetic field, but actual flips, are called geomagnetic reversals, and it's when the whole orientation of the magnetic field of the Earth flips. It's crazy. Speaking of crazy, the biggest mass extinction that we know about occurred at the end of the Permian. It's often called the Big Kill or the Big Dying extinction event. Awkward pause.
In a remote Nevada desert, a team of investigators is trying to solve an old murder mystery.
So yeah, this looks good.
And I mean old. The victims were knocked off about 250 million years ago in an ancient mass extinction of the geologic period known as the Permian.
Based on the fossil record, this is probably the most profound extinction of animal life.
But what kind of a disaster could destroy so much life? One of the prime suspects is an ancient group of volcanoes, now dormant, whose remains lie in eastern Russia. Known as the Siberian Traps, these were no ordinary volcanoes. The Siberian Traps oozed lava for up to 1 million years, smothering an area about the size of the continental United States, in some places over 1 mile deep.
That is a lot of lava.
Sure is, but still, the lava was in Siberia, not in the rest of the world. So why would almost everything on Earth die? Marine geochemist Lee Kump thinks he's found the answer. The key is in how big volcanoes could change the environment, including the chemistry of the Permian Ocean. It all starts with the Siberian Traps, but the trigger is not the incessant flow of lava, which would burn and bury any life nearby. No, the real culprits are the gases that the volcanoes spew into the atmosphere, including one we've all heard of lately: carbon dioxide.
Carbon dioxide that's spewing out of these volcanoes is a greenhouse gas.
Greenhouse gases trap the sun's heat in our atmosphere, forcing the whole Earth to warm up. Of course, that's global warming. But it doesn't end there. Global warming would have heated the Permian Ocean, and when it did, ocean chemistry would have changed dramatically.
There's a difference between warm and cold water. Cold water can hold more gas than can warm water. And so this is fundamentally why we drink champagne and beer and soda cold rather than warm.
What's true for champagne, beer, or soda is also true for the ocean and one of its most important gases, oxygen.
Cold water can hold a lot of oxygen. Warm water can't hold much oxygen.
And if water loses its oxygen, things can go from bad to worse. Lee and his research team have seen this firsthand at Green Lakes in central New York State.
Hey Rob, you ready?
This lake is narrow and deep, and there's little wind. As a result, the deeper waters have lost their oxygen.
It's safe to swim in this lake as long as you stay above 70 feet.
Below that, the oxygen-free water has attracted a deadly form of bacteria.
There are bacteria that can thrive under those conditions, and those bacteria produce hydrogen sulfide. Hydrogen sulfide is a very toxic substance, and so the deep part of this lake is highly poisonous. This lake is a microcosm of what we think the ocean was like in the late Permian.
According to Lee's computer model, over time, the oceans would have become so full of hydrogen sulfide that in some spots, the deadly gas would have bubbled right out into the atmosphere, killing millions of creatures, not only in the sea, but also on land. The deadly microbes under suspicion aren't rare. They thrive wherever there's water and no oxygen. So, it starts with volcanoes spewing carbon dioxide. Next step, global warming. The oceans heat up and lose their oxygen. Nasty bacteria take over, burping out lots of poisonous gas. End result? Mass extinction. The Nevada rocks offer some support for the idea. This whole area was once at the bottom of an ocean, and tests on the rocks have revealed that in the years leading up to the extinction, the deep ocean water here had lost its oxygen. The next step will be to probe these rocks for telltale signs of that nasty bacteria and hydrogen sulfide. Until there's more evidence, the detectives won't all agree that the case is closed. But these experts are convinced that Earth's own environment could be the perpetrator of a mass extinction.
I feel like that video has just the right amount of cheese in it. Oh, and did you say the New York State shout out at Green Lake Park? I've never been there. It's like a giant kettle. That's really it. And very deep. All right, so we're going to talk about the 3 hypotheses for what caused 95% of everything to die. And you saw a bit of that in the discussion about the Siberian Traps eruption. And I'm not going to dwell on this too much because you're going to watch a whole video on it, but it is the largest known volcanic eruption to ever occur in Earth history. It resulted in a volcanic winter, meaning that there was so much ash and material that was sent into the atmosphere that it dropped global temperature even in summer times, resulted in really high concentrations of carbon dioxide. So there you have that double whammy of big volcanic eruptions of short-term cooling and long-term warming. The second hypothesis has to do with a meteor impact. And the scientist who is most closely associated with this hypothesis is Michael Rampino at Penn State University. Michael Rampino, I've seen him give talks where he basically tried to link every mass extinction to a meteorite impact. And he thought that perhaps the impact of a large asteroid or meteorite could have induced volcanism and actually caused the Siberian Traps eruption. However, there's not a ton of evidence to support this. There's not a lot of shocked quartz or shattered quartz or iridium anomalies around the Siberian Traps eruption. You're going to learn more about these two substances when we learn about dinosaurs. But shocked quartz is basically where a single grain of sand gets shattered at an atomic level. It's only found at nuclear test sites and meteorite impact sites. Iridium is also a rare earth element that is found in much higher abundances in extraterrestrial objects. So there's very little of these clues that indicate that there was a meteorite impact at this time. The third hypothesis is kind of interesting, and it involves a bit of the first one, and that is the 3-phase extinction that was discussed by scientists Paul Wignall and Jerry Dickens. And it's kind of a cool story. They believe that there was a 3-phase extinction that started on the terrestrial environment, then impacted the marine ecosystem, and then led to more terrestrial extinction. So how did this happen? So the first phase, that terrestrial extinction, is the result of the eruption of the Siberian Traps. So created tons of habitat destruction, acid rain, volcanic winter, right? Really bad time on Earth. So what happens is all of this heat and carbon dioxide eventually, over a period of about 1,000 years, gets absorbed, or 1,000 years or so, gets absorbed into ocean waters. When carbon dioxide dissolves into ocean water, basically it turns into a weak acid. So who cares? Well, the organisms living in the water care. Not only does that make the water more acidic, but also a lot of the heat from the atmosphere that comes from all the carbon dioxide that's emitted results in warming of the oceans, even at the deepest depths. So organisms that live at the bottom of the ocean are really sensitive to changes because it doesn't change down there. The temperature is constant year-round. The gas content of the water is constant year-round. The light is zero year-round, right? So any sort of perturbation to bottom waters really upsets those organisms and can result in a marine extinction. So then what happens next is basically the surface of the earth gets warm enough to result in a process called methane hydrate dissociation. Methane hydrate is like frozen methane. It's found in all of the areas that you see here in orange. It's a crazy substance that was only discovered in the 1990s. So there were petroleum companies, and they kept seeing this funny little blip, this squiggle on their seismic sonar mapping of the seafloor. And eventually, in 1992, I believe, off the coast of in the North Sea here, one of those petroleum companies drilled into it. And what happened was huge bubbles of methane came bubbling up to the surface, and the drill rig actually sank. So let's talk a little bit more about methane hydrates. Here is what happens when methane hydrates become unstable. They're only stable when temperatures are cold and pressure is high. So when that petroleum company drilled into the methane hydrate in the North Sea, they removed all the pressure from all the overlying sediment, and they caused an explosion of methane gas. So the frozen methane turns back into methane gas very violently when it's either too warm or when the pressure is dropped. We can see this happening on land today in northern Russia. And these are huge pockmarks that have occurred in Siberia in Russia and have been mapped over a period of time. They are getting more and more common. So here you see some of these small areas where basically the frozen methane in permafrost, as the surface of the earth warms, eventually permafrost begins to melt, and methane hydrates that are trapped in that permafrost go from being, again, frozen methane back into being gas. And you have this massive explosion as you have that gas content shooting up from below and pushing out all of the overlying sediment and rock. Some of these very extensive, couple 100 feet deep, no joke. And so then when folks go, and no one's seen it happen, which is kind of cool, but there's always this lingering smell of methane when you get there. So these icy solids, basically, if the earth gets too warm, and the surface waters get too warm, and you can see that these are all right around continental shelves right off the coast of the continent, what will happen is that they return to gas, and that drives heat, because methane, remember, super powerful greenhouse gas. All of a sudden now we're putting way more greenhouse gas into the atmosphere, and that's going to just keep accelerating this positive feedback cycle that we see here.
I'm participating in Neptune at the gas hydrate sites. Gas hydrates are methane in form of ice. They look like snow, basically. They form, in that case, close to the sediment surface under specific temperature and pressure conditions. It's a huge compact energy source, which is of great interest to both climate investigators and also the energy companies. People think that they might contain more energy, more fossil fuel energy, than all the other fossil fuel sources on land. For us, it's very important to see whether there's an effect of climate change, slowly increasing bottom water temperatures, on the release of methane. It's very important to understand the behavior of gas hydrates under different temperature conditions, because if you slowly increase bottom water temperature of Canada, that kind of sudden release of methane from these gas hydrates could occur. That's one thing. It's interesting to find out whether small seismic events or larger seismic events, small earthquakes, have an effect on methane release. Or maybe it's possible that we can detect an upcoming earthquake because before it happens, slowly or just short before it happens, more methane is suddenly released and we don't know why. Had it happened before, about 8,000 years ago, after the last glacial time, one instability occurred in northern European waters around Norway. You can imagine that when there's, like you have snow in the sediments and suddenly all the snow is gone. That would mean the sediment sits on nothing. And that as a result of that, the sediment can suddenly slide down the continental margin and like creating an avalanche. And that affects, if it's on large scale, this avalanche can then create a tsunami wave. And that's what probably happened at that time. And that tsunami caused a wave which was more than 30 meters high at the Norwegian coastline. And most probably the gas hydrates were the reason for that. Because of global change, the bottom water temperature slowly starts to rise. So we must be careful. We don't know yet what can happen, but we definitely know that it can happen again.
Heartwarming. So methane hydrates seem to be too volatile and for it to be used as an energy source, but they definitely were attempted to use an energy source years ago. So since their discovery in the 1990s, geologists have linked methane hydrates to plenty of events. It's kind of hard to detect. You generally need a big shift in your carbon isotopes when you look over an event because this carbon that's in methane hydrates, because remember methane is CH4, tends to be isotopically really light, which you'll learn more about in the video that you watch. So that brings us to the end of the Paleozoic. We discussed in this chapter that the Appalachian Mountains were uplifted in 3 orogenies, right? We have the Taconic orogeny, Acadian Caledonian orogeny, and then finally the Alleghenian orogeny, the very end of the Paleozoic. We saw throughout the Paleozoic, as we moved out of the Precambrian eons and into the Phanerozoic eon, diversification, especially of marine invertebrates, eventually to vertebrates as organisms overtook the land. There were some major mass extinctions that we talked about. So there was one in the Ordovician. We didn't really talk about the Devonian extinction, but then we wrapped up with the biggest of the extinctions in the Permian. And what happens at the end of these big extinctions is that it leaves opportunity. And this is true throughout geologic history that, like if you think about the stromatolites, they figure out how to take something that's super common, like carbon dioxide, and turn it into their food. So these evolutionary niches where organisms basically figure out how to make a living with what's essentially junk leads the way for completely different dominant organisms on Earth. And what you'll see in the Mesozoic, it leads to the rise of reptiles in the Mesozoic. So good times. Welcome to the end of Unit 3.